Hey guys, my name is Jaden Pruitt, and today I will be talking to y'all about our trebuchet design and model approach we took on this project. My group members are Alexis Ritchie, Tipper DeWitt, and Gage Nyman, and we'll kind of go into detail later about what we exactly did. I'm going to let Alexis take over the outline for today. Alexis.
Alright, so today we're going to be talking about the trebuchet history, and then later we will go into the SolidWorks introduction and how that played a part in our design and helped us create all the parts that we have listed here. After we go through and talk about each part that we created, we will then go on to discussing how we put them all together, the mating process, and the assembly of all of it. Then afterwards, we will show you the calculations to back our assembly and measurements, and then we will go on to discuss each of the simulations that we had ran on the computer, and then later we will ask for questions. And now I'm going to hand it off to Gage Nyman, and he will talk about the history of the trebuchet.
Hey there, y'all. The history of the trebuchet starts in the 12th century. It was designed during medieval times as a siege weapon. So as you see up in here, it was powered by men. It was a very large structure, and it was used to launch stone projectiles to castle walls to destroy them, so they could invade the castle or the city, whatever they were trying to accomplish. The trebuchet, back in the day, it would launch stone projectiles up to 200 pounds, and they would go as far as 200 yards. So now I'm going to pass it to my team member, Tipper DeWitt, to speak on some of the parts that we modeled.
So to model the trebuchet, we decided to go with SolidWorks. So we really felt like this was the best path for us because we've been learning about it in class, and we wanted to apply what we've learned. And I'm going to start discussing some of the parts that we modeled in SolidWorks. So I'm going to start with the base. So the base is a really important part of the trebuchet. A lot of components go into it and considerations. The weight and the area of the base of the trebuchet is really important because we didn't want it to be too light and it throw itself. And it really goes into the accuracy of the throw. So the base of the trebuchet is really important. So here we have some of the we have two views, and it just shows some of the dimensions, 40 by 10. And now I'm going to go into the support arms. So again, the support arms are really an essential part of the trebuchet. Like the name suggests, it does support, it is a really big part of the structural component of the trebuchet, and it goes into the stability of the trebuchet too. And it also provides a suitable angle for the launch, which is really important too. So I'm going to go to the next slide, and here's two of the views, just some of the dimensions and everything. And now I'm going to hand it off to Alexis, and she'll talk about the connector of the support arms.
So the connector of the support arms is just what Tipper said. It holds the support arms together and provides more stability and accuracy for whenever the trebuchet is launched and the long arm goes and the sling is thrown forward and the projectile can then go. It helps hold everything together, make it more solid and accurate for the release. This is a slide showing the support arm connector, and it has the holes that we would use to connect it to the support arms to hold everything together. Next, we'll go on to talk about the axle. The axle is the main point of rotation for the long arm, and that is what that tilt provides it to throw forward and make it go further. And then we'll go on to the slide to show the axle, and this is how we created it and built it. And next, we'll talk about the launch arm. Launch arm is the part that I've been talking about as far as the long arm. It is what it's holding onto the sling, and it throws the sling forward, providing the projectile to go out, and it has a 5-to-1 ratio, which provides more of an advantage and leverage to throw it forward. This is a display of the long arm / launch arm that shows what we built in SolidWorks, and it has a notch right here sticking out, so that way whenever it is thrown forward, the sling can then slip off and allow the projectile to go forward, providing it full circulation of motion, so that way it doesn't lose momentum. And next, I will pass it off to Gage Nyman to talk about the counterweight.
Hey there, y'all. So the counterweight subassembly consists of three main parts, as you see here in the top right of the slide. The three main parts are the connecting rod, the connecting beam, as well as the weights that will attach to it. the first part I'm gonna talk about is the connector axle. It is a circular rod with two end caps that will connect the connector beams. Here's a few slides or a few pictures of it. As you see here, there's two different diameters. The outer diameter connects it to the connecting beam and ensures that it doesn't slip off. Now I'm going to talk about the connector beam a little bit. This is the connector beam shown in this other subassembly. As I said earlier, the connector beam connects the connecting rods together. Here's a few views of it to show you some dimensions. Like I said, these two holes are where the connecting rod is going to be connected at. Now I'm going to talk about the weights. The weights were modeled to resemble barbell weights. So if you look here in these slides, they're circular with a hole in the middle of them to be connected to the connector rod. And this allows for easy use, taking them off, putting them back on to alter our weights if we needed to. And now I'm going to pass it to Jaden to talk about the assembly.
Okay, so with the assembly itself, we used a mixture of coincidence, concentric, and parallel mates. With that, I'm going to show you a few pictures. So here we used a parallel mate to the base, and then we also made a representation of what screws we would use in putting this together. So over here we have a screw that represents about 2 3/4, and we have a screw here that's about 2 inches. So the 2 3/4 will go into the base at the very bottom, and then the 2-inch ones will go into the supporting arm or beam itself. And with that, we had to do a lot of parallel and coincidence mates to the inside of the larger diameters of the axle, like they were showing you earlier. And in our SolidWorks, we can actually make this move, so you can see the release points shown here. So next, I'm going to show you the exploded view, so you can see those parts and exactly what I'm talking about. So with this exploded view, you have the first start of the arms coming together, then the screws set into the arms, the supporting beam, as the screws we were talking about earlier, and then the trebuchet long arm itself and the counterweight will be connected together with the smaller axles to give it more of a pivot at the end. It helps with launching. So next I will hand it off to Gage with our calculations and everything behind that.
Hey there, y'all. We had to use several different equations in our design process. The first one is shown in the top left of the slide. It is for the constrained horizontal motion when the trebuchet starts. This is here, so it will be on a flat surface, so the projectile will not be able to go anywhere but on the horizontal plane. That's what this equation in the top left represents, and we use several variables in there like the length of the long arm, the length of the sling, as well as the height. All those played a key factor in how efficient our trebuchet was. The second subset of equations is on the bottom left, and this is a position and a velocity equation. They consist of the same variables as the equation above, but they're just arranged a little bit differently due to the different type of motion. This motion is a circular motion from when the trebuchet starts and the counterweight is released, and these equations represent that circular motion, and the angles and the height as well as the lengths all play a key factor in the efficiency of our trebuchet. Now I'm going to pass it to Jaden Pruitt to talk some more about our project.
So with our trebuchet simulations, me and Gage were talking about it, and we found that this would be the best representation, especially with what calculations and how difficult they can get. Ideally, taking a model approach, we did a trial and error on this simulation, and with that trial and error, we decided that our base for the one over here, our base arm was a little bit too long, and the counterweight arm was a little bit too long. So we took that into consideration, but I would also like to mention that we used a constant in the mass of the projectile. The goal of this whole project was to throw a paper ball into a trash can around 23 foot. Now, what I did is we took art paper, wrapped it up into a ball, and when we did that, I weighed the paper itself and then converted to pounds here shown. This would be considered a constant in the simulation. Now the simulation has about a 26% error. We took that in consideration also. 45 degrees is the ideal release point. Yes, it may not be 45 degrees in real life, but for the simulation we made it like that so we could have a really good idea of how our ratio to our calculations will work. Also, another thing I would like to mention, he was talking about the counterweight weights. With that, you have the 8 pounds here shown. And with those 8 pounds, that represents about 4 of those circular counterweights. And with that, we came out with about a 44.9% range efficiency. And yes, there is a percent error with making this, but we felt as if this would be the best ratio to continue our calculations. So I'm going to go ahead and wrap up and give it to Tipper. And thank you all.
So that's the end of our presentation. We really enjoyed this project as a whole. It really allowed us to apply the things that we've been learning in all of our classes into real life. So since this is a recorded presentation, if you have any questions, don't hesitate to email us. Here are some of our emails, and thank you for watching.